This is actually these slides from my keynote speech at IEEE CAMA conference in what is IEEE AP Society. CAMA is Conference on Applications and Measurements of Antennas. That was late last year. So it should be fairly up to date. Right, so I'm talking about complete beam steering.
Sir, your mic is muted.
Okay, so this is about near field metasteering, a method for complete steering of the beam of any fixed beam antenna. I don't know whether you heard or not. This was the keynote speech I gave in IEEE CAMA conference late last year. So first, let me define what I mean by complete beam steering. That is change in beam direction almost continuously within a specified range. Change in both angle of the beam, that's elevation angle and azimuth angle. Sometimes this is called 2D beam steering because we are changing both variables of the direction. Some people call it 3D beam steering because it happens in 3D space. I don't know what's going on with this. Microphone. So let me repeat. This is about complete beam steering, that is changing the beam direction almost continuously within specified range. So it's not beam switching. It's not having finite number of beams and switching between them. That's the difference. And change in both angles of the beam, elevation angle and azimuth angle, or sometimes called zenith angle and azimuth angle. So change in two variables of the beam direction, so called 2D beam steering. And some people call it 3D beam steering, so the beam moves in 3D space. But I think 2D beam steering is the right word mathematically because you are changing two variables, not switching between discrete set of beams. Okay, so how do you do? Okay, I know what happened is if right. So suppose you have an antenna like this, any fixed beam antenna, right? Any fixed beam antenna, and you want to steer the beam. Let me set up the slideshow. I think that is not. Suppose you have an antenna with a fixed beam like this and you want to steer its beam. So there's only one way to do it in the past, in the whole history of antenna engineering. This is the only way to do it. You add a mechanical system, mechanical tilting and rotation system to tilt its beam, right? And it works for any antenna with a fixed beam. Now this is not easy. You need to change the input, the feed, the structure, of the antenna, make it flexible, and also for a large antenna, you need very, very expensive mechanical tilting arrangement. If it is a small antenna, then still you need quite a bit of mechanical tilting, but it's easier than large dish antennas like this. Okay, now there's another method. Now there's another method to steer the beam of any antenna. This is called metasteering. This is called metasteering the beam, and it works for any fixed beam antenna. So what you do, you take your fixed beam antenna, that is this blue box. Okay, it doesn't have to have this shape, it could have any arbitrary shape. And then you have two metasurfaces above it. You place two metasurfaces above it. These are phase gradient metasurfaces, and you rotate them. You can see how they are rotated. The top rotation is called co-rotation. Both metasurfaces are rotated in the same direction. So when you do that, you change the azimuth angle of the beam. So the beam goes on a circle, and you don't change the elevation angle of the beam. The second type of rotation is called counter rotation. You can see the two metasurfaces are rotated in opposite directions. Uh, Lower one this way, upper one now going clockwise. When you do that, the beam azimuth angle of the beam is fixed. The elevation angle of the beam changes. But in practice, you have to change. You need to change both, right? From one direction to another, you want to change both angles, and that you can do by superimposing a linear superposition of these two motions. Uh, so you can see that there's no changes to the antenna. The antenna is fixed. Antenna interface, RF connections are fixed. You don't have to remove the antenna. In fact, you don't have to even touch the antenna. You can just leave it alone. And you can retrofit these metasurfaces and the rotation system. Also, there's no mechanical tilting, so it doesn't take space. The whole system is low profile, can be concealed by a box, and that is basically what is now called metasteering. So we will find some more details about this. It works and has been applied.
Sir, your mic is muted.
Yeah, I got a call. So now this is more of the same figure. This can be applied in any frequency, RF microwave, millimeter wave, terahertz, or even higher, as long as you are able to develop phase gradient metasurfaces. Uh, so you can use any antenna as the base antenna. It's completely stationary, a fixed beam antenna. And I said these two special design methods are placed in the near field, very close to the antenna. You don't have to go very far. You can put this in a wavelength or fraction of a wavelength sometimes. The gap between these two, and the gap between metasurface is also sub-wavelength. So this method is very low profile, and obviously these metasurfaces are in the near field of the antenna, hence the name near field metasteering. So we published the first paper on this method we published with my PhD student in IEEE transactions in 2017. Since then, there's a lot of citations, I think some 200 papers cited this, and a lot of companies are using that method for to develop commercial products. I will show some of them. It's been used everywhere now, from North America to Asia, Europe, uh, etc. So what is the history of this? How do you describe these metasurfaces? I said that each metasurface is a phase gradient metasurface, right? In fact, they behave like a prism. So this whole structure behaves like a so-called far-field prism. That's an optical device, and that's an optical method for scanning laser beams. Suppose you have a laser beam like this, and you put a prism, a standard prism, and the prism will bend the beam. It will bend the laser beam, right? Now, if you rotate the first prism, ignore the second prism. If you rotate the first prism, it will still bend the beam, and you can steer that beam, and you can create a circle by rotating the first prism. Then you add another prism, second prism, and put it like this. So the path length or the thickness increases in both of them in the same direction. Then the first prism tilts the beam, and second prism tilts even more. So you get double the tilt. If you rotate the second prism without rotating the first prism, then you can, first one tilts the beam, other one tilts it back in the backward way. So then you get the straight beam. For any arbitrary rotations between the two, you can steer the beam to any direction within a large cone. So this is called Risley prism. That's a very well-known concept in optics, and you can even buy Risley prisms off the market. But we are not in optical wavelengths. We are not in the far field. We are in the near field. At micro frequencies, using prisms is very difficult because the prism is like a dielectric wedge that is very bulky. So to implement this in the near field metasteering system, what we did was we mimic this bulky prism by a printed circuit board, very thin printed circuit board. So if you go back to the previous, this antenna mimics the laser source, the first metasurface, the lower metasurface mimics the first prism. So it's a flat prism, and the second one mimics the second prism. It's another flat prism. So what we need are two flat prisms, and the source is the RF antenna. So these prisms actually, what does they do? In optics, they have a differential path length. The differential path length means the differential phase shift, right? So these prisms have to give variable phase shift along the length to behave like a prism. Phase shift here is smaller, phase shift here is large. It should give a prism-like phase shift, spatially linear phase shift with a linear gradient or a linear slope of the phase shift. So what it does is it actually transforms the antenna phase, near field phase, to something else. The first prism, first metasurface, and the second one does transform that phase, near field phase, to another. So the generic principle behind this is called near field phase transformation. Near field phase transformation is that you design a phase transformation surface. You can call it
Again, you are muted, sir.
um, so this let's get in and out. So you have a near field phase distribution theta I, that is a function of x and y. That is near field phase distribution created by the antenna. You want to transmit to something else, a more desirable near field phase distribution theta out, also a function of x and y. For that, you need a large number of elements here. For example, if it is a metasurface, each cell in the metasurface give a phase shift equal to theta O xy minus theta I xy, right, at that location. So that is the idea of near field phase transformation. Arbitrary phase distribution in the near field of any antenna, that's what we got now, is transformed to a more desirable phase distribution at the output of phase transformation surface. So the history of this is actually related to resonant cavity antennas. If you make a very simple resonant cavity antenna like this, one dielectric slab, a ground plane, and a feed, and this is the phase animation. We found that the directivity of this kind of antenna is actually not the best. The directivity and therefore aperture efficiency and gain are much lower than one would expect from the size, from the area of this kind of antenna. And we were investigating why. Okay, what is the reason? Now, if you look carefully, you can see that the amplitude distribution of the near field is not uniform. That is one issue. If you have a uniform amplitude along the whole length, then you get the maximum directivity from antenna theory. Not only that, you can see the phase distribution across the aperture is extremely non-uniform. Highly non-uniform aperture phase distribution. Actually, it's from the middle to some places, the phase change is 180 degrees in some antennas, so they cancel each other. So then what I wanted to try those days is to answer this question: can they be improved by transforming this non-uniform near field phase distribution to a more uniform near field phase distribution and get more directivity, right? Using some sort of a near field phase transformer. That was the research question. So we try to answer, forget about this because we have already seen this. So to answer this question, I will skip all these RCA things because I had to explain what resonant cavity antenna is in the conference. Now this is the same slide, right? Can they be improved by transforming the non-uniform near field distribution to a more uniform one? So the answer was, after our research, yes, it can be done by using a near field phase correction surface or near field phase correction device. And if you place the phase correction structure a little bit above the resonant cavity antenna, a fraction of a wavelength above that, and design it properly, you can significantly improve the directivity and also sometimes can reduce side lobe levels. So our first paper on this came out in IEEE Transactions and Transient Propagation in 2015, called Dielectric Phase Correcting Structures for Electromagnetic Bandgap Resonator Antennas. And the second paper is a low profile planar, printed planar phase correcting structure to improve direct to radiation characteristics of electromagnetic bandgap resonators. So we did not call it a metasurface those days, we just called it planar phase correcting surface. Now we call them metasurfaces as the terminology changed. So this is how we did it. In fact, 3 ways. In the first one, the near field phase correction has been achieved by this, an all dielectric variable height stepped phase correction structure. And this is, in simple words, it's a lens. It's a microwave lens. It is not a flat lens, but it's a microwave lens. We stepped it because for the ease of fabrication. Otherwise, analytically, its shape could be more continuous. This is a structure we published in a physics journal, Journal of Applied Physics, for another antenna. So ideally, the structure, all dielectric structure, should have a shape like this. In most of the antennas we dealt with, the phase error has rotational symmetry, so the correction surface also have rotational symmetry. And this one, as I said, we step for the ease of machining. So in the middle, it gives, the structure has longer effective length, right? Electrical length, so creates larger phase delay, and here less phase delay. More phase delay here, less phase delay here. And this phase delay compensates the phase error of the antenna and produce a uniform phase distribution at the output. But both of this method using dielectric to do it is bulky and not very exciting. So later we made a metasurface or a printed phase correction structure that mimics this, that behaves exactly like this. But this is a very thin printed planar printed circuit board, or now we call metasurface. So let's see how we design this. So this is the first antenna. The resonant cavity antenna is this pretty lousy, simple resonant cavity antenna. This is the PRS. This is the resonant cavity. This is the ground plane. This is the feeding patch. Okay. So that's the antenna that has poor non-uniform phase distribution. And this is our phase correcting structure. Big machine lens, bulky lens. And this is the improvement in directivity. So this is the directivity pattern, not normalized on both E and H planes. In the without the phase correction surface, the pattern is shown by the blue line. With the phase correction surface, the radiation pattern is the green line, and you can see the improvement in directivity. It's about 9 dB increase in directivity because of the phase correction surface, because we are correcting the surface phase non-uniformity. We don't do anything to the amplitude. Amplitude non-uniformity is still there, but just by correcting the phase non-uniformity, making the phase uniform, we got this increase in directivity. Now this is the printed one, Metasurface, printed planar, printed circuit board, and you can see how thin it is. This is a multi-layer printed circuit board. I think 3 layers of metal and 2 layers of dielectric, but very, very thin. And that mimics that bulky prism, bulky lens. So this is all you need. And this is the same resonant cavity antenna. We did not change the resonant cavity antenna. We only changed the correction structure. Now the whole antenna is less than 1 wavelength tall. And this is the top surface of our phase correction structure. These are the cells, unit cells. Of course, you see only the top part. It has 3 layers of metal. So you see only the top metal patches, and then there's the bottom metal patches that were identical. In the middle, there are other metal patches that are not the same, don't have the same dimensions. Now the performance, again, the same improvement. Same improvement. This is without phase correction. This is with phase correction. Again, about 9 dB increase in directivity just because of the phase correction. So what does this metasurface do? Each cell provides the necessary phase shift to make the output phase more uniform. The input phase is changes from location to location, right? And then we work out how much phase shift you need for each cell. An idea is like this gives an idea how much phase shift you have to change without changing the thickness. We do all that by designing these cells, phase correction cells. So you can see in our paper the details, how the cell structure, the nature of different cells, etc., cell parameters. So this is the effect of that with the phase correction surface. This is the original antenna. This is the phase non-uniformity you saw in the previous animation, right? You can see that the phase fronts are almost spherical because of the phase error on the surface. We don't want that. After phase correction, with the planar phase correction structure that we call Metasurface now, you can see the phase fronts are almost flat. Phase fronts are parallel to the antenna. That means uniform phase across the aperture, or at least most of the aperture, where the field strength is high. We don't correct all the way to the edge, but we correct the central part of the aperture, the important part of the aperture where maximum near field is maximum, what we call the hot spot, and that's why we are getting high directivity. And so that is basically the near field phase correction. A non-uniform phase distribution in the near field of any antenna can be corrected by a structure like this to a more uniform phase distribution in the output, and by doing so you can increase the directivity. When you increase the directivity, you can also get higher aperture efficiency and gain. So you can do the same thing to increase the directivity of a small antenna. There are a lot of articles about directivity enhancement of small antennas, right? Directivity enhancement of small antennas, like a patch antenna, slot antenna, any antenna. There are two ways to increase the directivity of that kind of small antennas. One method we discussed yesterday. What is the method? If you think backwards, convert it to a resonant cavity antenna. Okay. So the antenna with small directivity, like a slot or a microstrip, use this as the feed to a resonant cavity antenna, create resonance cavity, and that will increase directivity. Or that's another way to do it. Put a phase transformation surface and make the phase more uniform, because when you go a little bit above any of those antennas,
Sir, your voice is not coming. Sir, you are not audible. Hello? Hello, sir. Your mic is muted. Am I audible?
yeah, okay. I saw the problem, but the problem was not muted. Mic became disconnected.
Okay, no issues.
So I had to disconnect the USB and reconnect. Okay. So yeah, because the small antennas have spherical wavefronts, and just like the one you saw, it can be corrected, but you need space in both cases. So this is an example. You take a small patch or slot antenna, put a phase correction surface, you make the convert the spherical wavefront to a uniform wavefront, and you get additional directivity and gain. Now this is not a resonant cavity antenna, because there's no resonance um, just by doing that. So you don't need, it's kind of a lens. And also you can combine both of them together. That's what we did in the previous. We have a resonant cavity antenna, and then even the resonant cavity antenna, because it's a very simple one, has phased error, and that can be corrected using a phase correction surface. Can be corrected using a phase correction surface, so you get higher directivity. Okay, so this is a small antenna, spherical wavefront, and put a phase correction surface. When it is phase corrected, you have the phase fronts that are parallel to the antenna, uniform phase fronts, get higher directivity. Okay, so then get to steering the beam. Okay, what do you have to do to steer the beam? The second challenge was to steer the beam. So now we need these metasurfaces that has the phase gradient to tilt the beam, right? Each of them has to tilt the beam. So you need a phase gradient. We have design and prototype a large number of antennas like this. This was our first paper. It's a resonant cavity antenna and a near field metasteering system. It's linearly polarized. We steered the beam in theta by plus or minus 51 degrees. And in azimuth, you can steer all 360 degrees, no problem. In the elevation, the zenith angle of theta can be steered in this case by plus or minus 51 degrees, and the antenna has a gain of 19.4 dBi. This is another example that's a circular polarized radial line slot array antenna with near field metasurfaces, and that has a peak gain of almost 31 dBi-C, circular polarized, and we were able to steer the beam plus or minus 46 degrees from both sides. This is a smaller one. Otherwise, the metasurfaces are similar to this. And then this is a very wideband one with completely different type of metasurfaces. I will show you the details later if you can't see this. In this case, we use a wideband horn antenna and all dielectric metasurfaces. Got at millimeter wave frequencies. We got a gain better than 21 and excellent bandwidth. The other type of there are a lot of different type of metasurfaces. Hope I will have time to show you several of those today. This is another metasurface type. It's called all metal. There's no dielectric. This one is all dielectric. There's no metal. This one is all metal. There's no dielectric. Near field metasurfaces. Dual. We have some dual band ones. In this case, the base antenna is a horn and gain bandwidth of 6.4%. So that is some of the recent development in this area in my lab, and then I will show you some others work. Not a lot, but few very important work. So this paper, beam steering for highly transmitting hybrid metasurfaces and circular polarized high gain radial line slot array antennas. This is our antenna. That's a very good antenna. You can see the slots on an array, on a spiral. They produce very high quality circular polarization and high gain. So this can provide 35 dBi gain beyond what is possible from resonant cavity antennas. Then our metasurfaces are called hybrid. I will explain it later with some more figures. And this is another paper. These are the all dielectric metasurfaces, no metal. This is a project we have done with Australian Department of Defence and published with Defence staff and my UTS staff together. So that's all metal. Then looking one by one, what's the time? Okay, still have one by one. This is the original paper, some details of the original paper. So you need two metasurfaces, right? So this is a resonant cavity antenna. Base antenna is a linearly polarized resonant cavity antenna. And we need complete beam steering, so we need two metasurfaces. But also, this is not, base antenna is not really good antenna, so it has phase error. So we have to phase correct the error as well. So for that, we need another phase correction metasurface. So we need a phase correction metasurface to correct the phase, then the first metasurface to tilt the beam, and then the second metasurface to tilt the beam again. So you need three metasurfaces. But it turned out that you don't need three. You can combine two of them together. So TM1 here does both jobs. It provides phase correction and also the tilt. The upper one only provides the tilt. So the upper one is easy to understand. It's only the tilt. It is like a wedge, dielectric wedge or dielectric prism. You need to change the phase shift of these cells in one direction. Phase shift is uniform in the other direction. You can see all the cells all are identical. In one direction, the cells change, so the phase shift increases or decreases with the location. However, when the phase shift becomes 360, you can go back to zero, right? You can do phase wrap. So after 360, you don't need the cell with 365 degrees. You can go back to 5-degree cell. So because of that phase wrapping, it becomes a periodic structure in X direction. In the Y direction, it's a periodic structure, always, because they are the same cells. And in the Y direction, we don't repeat the same cells. Cells are different, so it's not the periodic structure, but after one wave, after full phase wrapping, it becomes periodic. That's why you can see the same pattern repeating. Now the others are form, etc., not that important. Yeah, these are the cells. Look carefully. Constant phase in this direction, progressing phase in this direction. Because of that, we need different unit cells. So you see only the patch size of the metasurface on the top layer. But as I said before, there are two other metal layers. The bottom layer patches are identical and the middle layer patches are different. So this is a typical nature of a phase gradient metasurface or linearly increasing phase shift metasurface that gives linearly progressing phase shift in one direction, uniform phase in the other direction. So that's the top one. This is the actual fabricated prototype, and then we rotate that. The bottom one is actually this. We have to combine this with the phase correction surface, right? If you just do phase correction, we need the surface like this. To get the beam tilt, we need something like this. And you can have, and then for the other tilt, you need something like this again. So you need this plus two of these. And what we did was we combined these two into one to do the phase correction and the beam tilt into one. The lower metasurface is like this. That's why it looks pretty unusual looking. And then the performance, this is a beam steering performance, the actual gain patterns. This is the both side direction when one metasurface tilts and the other metasurface tilts back in the opposite direction, you get the beam going straight up, theta equals 0 direction, and then by rotating the two metasurfaces in opposite directions relative to each other, you can steer the beam. And this is the 3 dB band from the peak gain value. We can see that the gain is within the 3 dB from the peak. Peak is 19.5, in the band of 3 dB within the peak over large range of steering angles. In fact, you can steer plus or minus 51 degrees, a total of 102 degrees without losing the gain below 3 dB from the peak. So that's our first design, the first paper in transactions. This is a later one, the circularly polarized one. Now the base antenna of this I already mentioned. It's a, you already saw this radial line sort array. And then we added those additional new metasurfaces. We call them hybrid metasurfaces because these are printed PCBs. So you can see the cells, printed patches in a dielectric, multi-layer printed PCB. But in addition to that, if you look carefully, you can see some holes along certain lines. Those holes are to get effectively negative phase delay. So that helps us to cover even wider range of phase errors, or when you are tilting, to get a better phase coverage from these cells. As a result, we got better performance with this hybrid by making holes along certain lines. So again, this is a periodic structure in this direction due to phase wrapping. The phase shift in the horizontal direction changes like a ramp. It increases progressively and goes back to original value due to phase wrapping, and then again increases from 0 to 360 degrees down to 0 again, 0 to 360 degrees, and so on along the horizontal axis. Along the vertical direction, there's no phase change, it's a periodic structure. So that is the upper metasurface. The lower metasurface has some phase correction as well. The phase error of this antenna is very small, so we don't have to correct too much, but there's a little bit of phase correction. That's why it is not identical to this. So the peak measured gain of this system is 30.9 dBIC because it's a circular polarized antenna. The arrangement is here. So RLSA is this one, the bottom layer, and then the first metasurface HM1 is this, and the second metasurface HM2 is here, and they were spaced by nylon or plastic spacers. The total height of the antenna from the bottom to top, including the stand, is 4.5 centimeters, so 3 wavelengths at the center frequency. Okay, I went backwards. So this is about the phase error of the circular polarized antenna. To correct the phase, first we had to probe the phase error. So we probe. You can do it numerically using CST or whatever software you have. Define a plane above the antenna. Normally the plane where you are going to place the phase correction surface or the first metasurface, in this case about 1 lambda naught, and probe the phase, and you can see that the phase is not exactly uniform. There's some phase error, and the phase error is as approximate rotational symmetry. Um, Therefore, you can make the phase correction surface to have rotational symmetry. That's quite good because then you can integrate that with our first tilting surface, because we are going to rotate that surface, right? When we need to steer the beam. So still it does the phase correction. So this is the actual phase. This is the actual electric field phase on this surface from x equals 0 to minus 180, going from here to minus 180 along this line from here to minus 180. You can see some phase error is not constant. Therefore, the correction phase should be the opposite of that, right? We need to add this to this, the negative of that, and that is the correction phase we need to add from the phase correction surface to correct this and make the total phase 0 before steering. And that's what we did with the first phase correction surface. Okay, so it's just a better view of those. Actually, now you can see those holes here. Can you see the holes? So along this line, there are no patches. The, the patches increase the phase shift. The holes decrease the phase shift. If you don't have anything, then it is just a dielectric slab that has a certain phase shift. When the wave propagates through the dielectric slab, when you add metal patches, it increases the phase shift through the slab due to the effect of the patches. And when you drill holes, the effective dielectric constant of these unit cells decreases, so the phase shift decreases. So that is like effectively getting negative phase shift relative to the substrate. So some of the parameters, the maximum beam tilt was 14.6 degrees. The maximum gain I already mentioned. The axial ratio is a way of measuring how good circular polarization is. This being a circular polarized antenna, and it's less than 3 dB across the whole 3 dB beam width, even when the beam is steered. And the height of the system it's already mentioned, 4.5 centimeters or 3 lambda naught. So some more details you can find in this paper. These are the patterns from that prototype. As we steer, that's the bow side direction. In this case, we get the maximum gain when it is steered in the bow side direction, theta equals 0. And you can see as we steer the beam, the peak gain gradually drops. And these are the measured beam directions. The theta and phi of the beam directions. In fact, the phi value of the beam can be changed to anything between 0 and 360 degree, the theta value of the beam can be changed only from up to 40.6. Then it becomes highly distorted, or the distortion increases. Okay, so now at this point we wanted to increase the bandwidth. In fact, our defense collaborators wanted to increase the bandwidth to enormous values like 40% of this kind of system. So we made it a little bit simpler, like use a rectangular horn as the base antenna, and made it more like the original Risley prism, and use dielectric blocks, actual dielectric blocks for the phase transformation. It's not exactly a prism. There are some steps for machining purposes, but we built the prototype. The rotation system was built by the Australian Department of Defence, and we integrated them together. We call them step dielectric phase transformers. They are basically dielectric wedges with steps, and we got excellent beam steering in theta, complete beam steering, theta between minus and plus 52 degrees, and a fantastic bandwidth. It covered the entire millimeter wave band from 26.5 to 40 gigahertz. That's more than 40% bandwidth, with a variation of, so with a scan loss of 3.6 dB. Now this is additional information now, because this is a very wide band antenna system. The gain depends on the frequency, and these curves are for different beam directions. That's the variation of the gain when you change the beam direction at that frequency. Usually it's like 2 dB or less beam variation when you steer. Only in one case, I don't know why I said here 3.6 dB scan loss or maximum, because the data we have here, the maximum scan loss due to steering is 3.2 dB. That is only this frequency. A lot of other frequencies is much less. So that's very good complete beam steering. So that's another transaction paper in 2020. So I think we are taking the break, usual break 15 minutes. Any questions about these antennas?
So audience can ask their doubts. I think
Hello?
yes.
Hello, sir. I have one doubt regarding this near field. When you adding,
Could you speak a little bit louder? Sir, speak. The volume is very low here.
am I audible, sir? Hello?
Yes, yes, yes. Speak.
Yes, sir. When you put a metasurface in the near field, will it affect the input impedance or will it change, and what will the impact of it, sir?
If you play, if if you design it properly, it should not. Um, because they should not be reflecting.
Yes, sir.
Now, when you put a PRS, when you're making a resonant cavity antenna, when you put a partially reflecting surface, it can change the impedance of the feed antenna, because
Ye-
that is a reflecting surface, right?
Yes, sir.
but these are not supposed to be reflecting surfaces. So all these cells in the metasurface are supposed to be totally transmitting, or at least close to ideal transmitting elements, not reflecting. So
So
the
is there
transmission
any
coefficient of the cells has to be, normally we want them to be greater than minus 1 dB. Some of the worst ones could be minus 2 dB, and we try to avoid cells that are reflecting. That is very important when we design the cells, phase transformation cells. They should be transparent, not reflecting. If you
so is there
design it
any
that way,
distance criteria, sir? So like at what distance we should keep? So because near field in the we are saying it's in the near field, so the near field can extend over a certain region. So where we place the near field, do we have any criteria for that?
still you can, when you design the cells, you can use some far field approximations. The cells are designed as unit cells using the eigenmode solver, for example, unit cell excitation in CSTO and CIS.
Yes, sir.
Apply apply the wave from one mode from one end and try to get the phase shift from one port to the other. Um, but at the same time, you have to make sure that the reflection is less. Because in
Okay.
a typical unit cell design, you have the scattering parameters, right? The input reflection and the
Yes.
transmission.
Yes.
And you need to optimize the cells so that the reflection is very small. If you design it that way, then you don't have to worry, even if they are in the near field.
Okay, sir.
Okay, so you're going to take the break now. What's the time now?
Okay, sir.
5:32. So we will come back in about 15 minutes. Okay.
Okay, sir. Okay, thank you, sir.